here is a beautiful theoretical question on parallel plate capacitor. Do you remember how to write the capacitance of a parallel plate capacitor? It is C equals A epsilon naught divided by D. A is the plate area, epsilon naught is that permittivity of vacuum or air, and D is the separation between the two plates. So, A epsilon naught divided by D is the formula for writing the capacitance of a parallel plate capacitor. If the medium in between the two plates is not air or vacuum, then you will have to even write the dielectric constant of the medium that you have taken, that is epsilon r, and then the capacitance becomes A epsilon naught epsilon r divided by D. Fine? Okay. So, now let us read the problem. A parallel plate capacitor is charged and then isolated from the battery which was used for charging. The effect of increasing the plate separation on these three things, charge, potential and capacitance respectively, are. Which increases, which decreases, which remains constant is, I think, what we are supposed to select among the options. But the order in which he has taken up each one of them is charge, potential and then capacitance. Fine? Okay. Now, I told you A epsilon naught divided by D is the formula for the parallel plate capacitance of a parallel plate capacitor. After having charged, if you isolate that capacitor, if you remove the battery, then there is no question of charge being further added or taken away from the capacitor. As long as the battery is connected, there is a liberty for the battery to either send some more charge on the capacitor or take back the charge which is already on the capacitor. But because the battery is disconnected, capacitor is isolated, the charge which is now present on the capacitor plates is going to be intact, right. So, charge remains constant is for sure, whether you increase the plate separation or you decrease the plate separation. So, that I think eliminates one of the options, because the charge increases is ruled out. So, now you are left with three options in which the charge has been shown to be constant. The second thing which has been taken for discussion is potential. Let us postpone it for a short while. Let us think of the capacitance. A epsilon naught by D is the formula for capacitance, and you have increased the plate separation. See, increasing the plate separation. So, if you increase the plate separation, D becomes much more and the denominator becomes more, and therefore, the capacitance decreases, and that I believe should eliminate a couple of more options there. We had already eliminated this. We were left with these three in which the charge was shown to be constant, and now we were referring to capacitance, and capacitance, as we agreed, will decrease because of increasing the plate separation. Unfortunately, there is only one option in which he has given capacitance to increase, and capacitance, I told you, will decrease. So, this option is also ruled out. This was ruled out because of charge, this is ruled out because of capacitance. Now, you are left with only these two, and in both of them he says the capacitance will decrease. Now, let us use C is equal to Q by V or Q is equal to CV. Charge is going to remain constant, capacitance will decrease, therefore, the potential should increase. Charge remains constant, potential increases and capacitance decreases. So, the right option here is B. One more simple network on capacitors. So, let us read it. So, the charge deposited on 4 microfarad capacitor is to be found. It is a very simple network with one battery and a couple of capacitors there. What you can notice is this 4 microfarads and 2 microfarads are connected in parallel. Therefore, their combination results 6 microfarad capacitor. Now, you will be left with a circuit in which there is a battery of 12 volts and 2 identical capacitors of 6 microfarad each. So, what should be the drop in each one of them? The drop in this 6 microfarads should also be 6 volts, and in this 6 microfarads should also be 6 volts. Now, there are 2 capacitors which are in parallel, and across whom the potential drop should be 6. I hope I am clear. So, now you know the potential drop across this capacitor and you know the capacitance. So, you can find the charge deposited on this by using the formula Q equal to CV. C is 4 and potential drop I said is 6 volts. So, that makes your answer 24 microcoulombs, and that B option is perfectly correct. So, it is a simple network, these two are in parallel. So, if you add them you will get 6 microfarad capacitor, that will reduce the given network into only 2 capacitors of 6 microfarad each with a 12 volt battery connected. So, the drop across each one of them should be 6 volts. Knowing the drop and knowing the capacitance, you can find out the charge. 24 microcoulombs is the charge deposited. So, here is something about earthing which I would like to share with you people, and that is the reason I have taken one problem also here. Let me tell you that whenever you connect a conductor to the earth, please remember that you cannot speak anything about the charge. What charge will go from the conductor to the earth, what charge will come from the earth to the conductor is not the one which you are supposed to decide. By connecting a conductor to the earth, the only duty of the earth there is to make the potential of that conductor equal to itself. And we usually take the potential of the earth to be 0. Therefore, the potential of that conductor which has been connected to the earth will also become 0. And to make the potential 0, it is the lookout of the earth whether to send positive charge or take away positive charge or send negative and take away negative is all going to be decided by the earth. So, please remember, whenever you see a conductor connected to the earth, take the potential of that conductor to be 0 and do not speak anything about the charge. Any charge may come, any charge may go. Let us read the problem. So, here area of each plate, there are 2 parallel plate capacitors, one formed between these 2 plates and another formed between these 2 plates. Area of each plate is 2 meter squares, so which means all the plates are identical. Separation D is given to be 2 into 10 to the power of minus 3 meters. It has been very clearly shown that this separation is large and it is double of that. A charge of 8.85 into 10 to the power of minus 8 coulombs is given to the plate Q. So, he has given the charge only to this plate. This is connected to the earth and this plate is also connected to the earth. These are the symbols for earthing. So, when you connect these 2 plates to the earth, earth will try to send whatever charge which is required in order to make the potential of this conductor 0. The potential of this conductor should also become 0 and the potential of this conductor should also become 0 because you have connected those 2 to the earth, right? Okay. But because you have given a positive charge to this particular plate, 8.85 to 10 to the power of minus 8 coulombs or whatever, the potential of this plate and this plate have already become slightly positive because they are in the vicinity of a charge which is positive. Therefore, to make its potential 0, you can say that the earth has sent a negative charge on these 2 plates. I hope I am clear. See, these 2 plates are in the vicinity of the plate Q which has been given a positive charge. So, automatically they have acquired some positive potential by virtue of being in the vicinity of this, and therefore, in order to make the potential of these 2 plates 0, earth will send a negative charge on both of them. Fine. So, now you have one capacitor. Moreover, what he has asked is the potential of this plate Q. Let me assume that the potential is V. So, there is one capacitor here formed between Q and P with a potential difference of V and 0 means V minus 0. That is a potential difference of V. And here there is one more capacitor also with a potential difference of V minus 0 which is V. And what you can see is both the capacitors have got the same potential difference. So, we can conclude them that they are in parallel, and if they are in parallel, their capacitance can be directly added in order to get the resultant effective capacitance, that is C1 plus C2. Both are parallel plate, so you can write their formula as A epsilon naught by D for C1. I am considering the one between P and Q to be C1. and the one between Q and R is C2, where you will be writing A epsilon naught divided by 2D, because the separation is 2D there, and that makes C1 plus C2 as 3A epsilon naught divided by 2D. Now, this is one single capacitor of capacitance 3A epsilon naught divided by 2D, on which there is a charge given and the potential difference is V. So, you can find out that V using the formula V equal to Q by C. Okay, so if you substitute the value of Q which is given here and C that we have written here, in which the area is known and D is known, you will get the answer 6.67 volts, and that makes your C option perfectly correct. So, here is a very important and a beautiful concept about writing the work done by a battery. To write the work done by the battery, you need to check what amount of charge has flown through the battery and what is the EMF of the battery. If a positive charge Q has flown through the battery from negative terminal to positive terminal and the EMF of the battery is V, Q into V will be the work done by the battery. Fine. So, let us read the problem and see how best we can use this here to write the work done. So, there are two capacitors C and C by 2, and they are connected in parallel with a battery of V volts. Find the work done by the battery in charging both of them. Express your answer as a multiple of CV square is what he says. As these two capacitors are connected in parallel, their equivalent capacitance will be 3C by 2, C plus C by 2, and the battery which is connected is of V volts. Therefore, the charge which must have flown through the battery is Q is equal to CV, that makes it 3C by 2 into V. Knowing the charge and knowing the EMF of the battery, you can multiply the charge by the EMF and say that the work done by the battery is 3C by 2 into V into one more V, that is 3C by 2 into V square, and he wants you to express the answer as a multiple of CV square. So, that makes 3 by 2 as the right option. So, D is the correct option here. But the purpose of taking this problem was not just to tell you this. Let me warn you one important thing here, that is, if you look at these two capacitors connected in parallel across the battery, you will come to know that the potential difference across this capacitor is also V, and even across that capacitor is also V. So, the energy stored in this capacitor is going to be half CV square, and the energy stored in that capacitor will be half C by 2 into V square. I hope you recollect that the formula for writing the energy stored in a capacitor is half CV square. The capacitance is C connected in parallel with a battery of potential difference V. So, half CV square is the energy stored in this, and half C by 2 V square is the energy stored in this. So, if you add these two energies, the total energy stored in the capacitor is going to be 3 CV square by 4. And this is half of the work done by the battery. So, which means if you just look at the energy stored in the capacitor and take it for granted that this energy is a result of work done by the battery, and simply declare that 3 by 4 CV square, that is option B, should be the work done by the battery, then you are going to be wrong. So, please remember, when the battery works in charging these two capacitors, half of its energy is lost in the form of electromagnetic radiation. If the wires have got the resistance, then they get heated up and the energy is lost in the form of heat, and therefore only remaining half is going to be stored in the capacitors. So, 3 by 4 CV square is the energy stored in the capacitors, 3 by 2 CV square is the work done by the battery. Fine. So, that was the purpose of taking this problem. So, here is another simple problem on a parallel plate capacitor. I hope you remember that the formula for parallel plate capacitors capacitance is A epsilon naught by D, provided the space between the two plates is air or vacuum, and it is A epsilon naught into epsilon r divided by D, provided you have filled the space with some dielectric. Let us read the problem. An air filled capacitor has a capacitance of 2 picofarads. The separation of the plates is doubled and the space between is filled with wax. If the capacitance now becomes 6 picofarads, what exactly is the dielectric constant of that wax which you have filled in between the two plates? So, what we will do here is, he has told you what all he has done. He has doubled the space, that is separation between the plates has been doubled, and moreover it has been filled with wax. So, we will write the capacitance formula for the two new capacitors that you have. First one, it is 2 picofarads equal to A epsilon naught divided by D. A is the plate area. I have written only epsilon naught because it is an air filled capacitor, and D is the separation. Now, you have doubled the separation and you have used the wax as a dielectric. So, the new capacitance 6 picofarads that he has assured should be written as A epsilon naught, epsilon r standing for the dielectric constant of that wax which you want to find out, divided by 2D. This has also been given. Now, what I will do is, instead of A epsilon naught by D, I will substitute 2. So, 2 gets cancelled and you get epsilon r as 6. See, A epsilon naught by D is 2, so 2 by 2 gets cancelled and epsilon r will be 6. Therefore, the dielectric constant of that wax that you must have used should be 6, and that makes D option perfectly correct. So, here is an excellent problem. I think let us read the problem first and then let me tell you what is the beauty of that. Two identical capacitors, each of 5 microfarad capacitance, are charged to 2 kilovolts and 1 kilovolt potential difference. So, there are two capacitors, they are identical fortunately, but they have been charged to two different potential differences separately by connecting two separate batteries. Their negative ends are connected together. When the positive ends are also connected, what will be the loss in the energy? So, here are a couple of things which I would like to share with you people. They may be your confusions. One is, see, this is one capacitor which has been charged to say 2 kilovolts, and this is another capacitor which has been charged to 1 kilovolt. Say this plate is positive, this plate is negative, this is negative and this is positive, let us say. Now, he says the negative ends are connected together. So, I have shown you the negative ends being connected together. This is the negative plate of one capacitor, this is the negative plate of the other, both have been connected together. I would like to give a break here in the problem and ask you, will there be any change in the charge on this capacitor or this capacitor, energy stored in this capacitor or this capacitor, potential difference between the two plates of this capacitor or this capacitor? Question is, you have two identical capacitors, we do not mind even if they are not identical, they have been charged to two different potential differences, 2 kilovolts and 1 kilovolts. This is the negative plate of one capacitor and this is the negative plate of the other. Both the negative plates are connected together. Will there be any change in any of the things associated with these two capacitors? What I mean is potential difference, charge, energy. And let me tell you that there is absolutely not going to be any change in any of these properties of these two capacitors. Nothing will happen to the charge on this nor on this. No change in the potential difference between the two plates of this capacitor, neither there is any change in the potential difference between the two plates of this capacitor. There will be no energy loss either here or here. So, everything will remain intact, and the reason for that is you have still not completed the circuit. You have only connected these two negative plates. They are at liberty to do whatever they want. They have been connected together, they can share charges, they can exchange charges, they can do whatever they want, but these positive plates are not going to permit them, because whatever is the charge on this positive plate will never allow the charge on this negative plate to become anything else. If you say there is 1 coulomb of charge on this positive plate, there should be -1 coulomb of charge on this negative plate, and same is the case here also. So, there will be no change in the energy, no change in the potential difference, no change in the charge. That is the reason he has said that when the positive ends are also connected, what will be the loss. So, now there is one more very important thing that I would like to share with you people. Now, I have connected the positive ends or positive plates of the two capacitors also. So, I have made the circuit now, circuit is complete. Now, things can change, but my question is, would you call these two capacitors to be connected in parallel or series? If you just look at the circuit, some of you may feel that the two capacitors must have been connected in series because they are end-to-end connection. Or if you see that the negative plates have been connected together and positive plates have been connected together, you may call the connection to be in parallel. But I would feel that this discussion is going to be meaningless there, because ultimately whatever you do, they will be in parallel and will be acquiring the same potential difference. So, you cannot call this to be series and the other one to be parallel, or this to be parallel and the other one to be series, right. So, there is nothing like series and parallel in this problem. You have two capacitors, you have charged them to different potentials, and now you are going to connect them. Do not bother whether you are going to connect them in series or in parallel, because ultimately they will happen to be in parallel and the potential difference across them will become equal. Until then, the charge flow does not stop. So, what is important is how is that you have connected, that is whether you have allowed the charges to get added up or you have allowed the charges to nullify each other. Like here, there is a negative charge here and there is a negative charge here, and by connecting the two plates which were charged originally negatively or positively, see the positive plates have also been connected together, you will only permit the charges to sum up. The positive charge on this plate will now sum up with the positive charge on this plate before it gets redistributed, so that the potentials of both the capacitors become equal, and same is the negative charge also, that will get summed up and then it will get redistributed on the two capacitors to make their potentials equal. So, what matters here is how is that you have connected. Had I connected the negative plate with the positive plate of another capacitor, then the negative charge on this would have nullified the positive charge on the other, and the leftover charge would have redistributed on the two capacitors to make their potentials equal. So, please remember, in this one single problem I have told you two discussions about the connections of the two separately charged capacitors. Do not call them to be in series and parallel, but be very careful about whether you have connected the positive plate with the positive plate and allowed the charges to add up and then redistribute, or you have connected positive plate to negative plate and allowed the charges to nullify each other and then allow the remaining charge to redistribute. And how does the redistribution happen? So as to make the potentials of both the capacitors equal. Fine? Okay. So now initially we know what was the energy. How is that you are going to write the energy initially? The initial energy was half C V1 square plus half C V2 square, where C stands for 5 microfarads and V1 stands for 2 kilovolts and V2 stands for 1 kilovolt. So, this was the initial energy, and now the final energy can be written only after having understood what will be the charges on both of them or what will be the potential difference across each one of them. So, you can write that common potential as Q1 by C1 equal to Q2 by C2. See, Q1 is the charge on this, so capacitance is C1 or you can say C. So, Q1 by C should become finally equal to Q2 by C, which means the charge on both the capacitors, see what I have written is the potential difference across this capacitor and the potential difference across this capacitor. I have equated them because finally the potentials are going to be equal. Okay, but because the capacitors are identical, the charges deposited on them are also going to be identical. Fine, and Q1 plus Q2 is the original charge Q. So, Q1 plus Q2 is the original charge Q, So 2q equal to q, and that gives you q equal to q by 2, where what is this capital Q? Capital Q is the charge on this capacitor plus charge on this capacitor. How are you going to find out the charge on each one of them? Their capacitance is known, the potential to which they are charged is known. So Q is equal to CV, 2 into 10 to the power of 3 into 5 into 10 to the power of minus 6, 1 into 10 raised to 3 into 5 into 10 to the power of minus 6, that will give you Q, and charge on each capacitor will become Q by 2. So now you know the charge, you know the potential difference. How do you write the final potential difference? By substituting this charge value in any one of these, because Q1 by C should be equal to Q2 by C. Fine. So you get the potential difference and you write the final energy. So knowing the initial energy, knowing the final energy, let me write the final energy for you if you want. So final energy will be half, C will remain C, and that final potential will be Q by small q by C, or you can say Q by C square and twice of this, because both the capacitors are identical, the charges that they carry are also identical. So half C V square, V is Q by C, that makes it 2 gets cancelled and it is Q square by C. So you know the final energy, you know the initial energy, you subtract, you will get the answer, and the correct option here is 1.25 joules. Yeah, so one last problem. How many 6 microfarad 200 volt capacitors are needed to make a capacitor of 18 microfarads and 600 volts? See, each capacitor is of 200 volts breakdown voltage, and you need to have a 600 breakdown voltage across the system. So that is possible only when you have 3 capacitors of 200 volts each, because the drop in one is going to be 200, the drop in the second is going to be 200, and the drop in the third is also going to be 200, which will make that 600 volts which you are going to connect across the system to be correct. But now you need 18 microfarad capacitance, whereas you have 6 microfarad capacitor each. And remember, you have already decided that you need 3 groups, or you need a group of capacitance, say C. So one C, second C, and then third C. I am considering all the 3 groups to be identical. Huh? So each group has got a capacitance of C, and 3 such groups in series are fit enough to be connected across 600 volts, because this group will have 200 volts drop, second group will have 200 volts drop, and so does the third group. Okay. Now, if you connect 3 such capacitors of capacitance C in series, please remember that the capacitance, equivalent capacitance of that series combination is going to be C by 3. So what we will do is, we will write this C by 3 as 18 that you need. See, you need 18 microfarad single capacitance, and we have already decided that there are 3 capacitors of capacitance C all connected in series. So the equivalent is C by 3, and that should give you 18 microfarad capacitance. Therefore, C should be equal to 54 microfarads. So your each group should have 54 microfarads total capacitance, and remember, each of them should be across 200 volts only. So that puts a condition there that the group should have all the capacitors connected in parallel and not in series. That group should have all the capacitors of 6 microfarad each to be connected in parallel, so that we can take it for granted that the 200 volts of drop which is going to happen across one group will be across each of the capacitors present in that group. There are 3 groups, each of capacitance C. So each group should have 54, yeah, fine. And then you have 6 microfarad capacitance each. So how do you get 54 out of 6? Is by connecting 9 capacitors in parallel. So each group will have 9 capacitors of 6 microfarad capacitance each in parallel, amounting to 54 microfarads, and there will be 3 such groups. Therefore, 1 by 54 plus 1 by 54 plus 1 by 54 is going to give you 18 microfarads. But each group has 9 and there are 3 such groups, so 9 3s are 27. I hope I am clear. So, 27 is the right option here. So, if you choose 27 capacitors of 6 microfarad and 200 volts breakdown voltage and connect 9 of them in one group all in parallel and make 3 such groups, you will get the desired capacitance also and the desired breakdown voltage also. So, 27 is the right answer.